Thanks a lot, Luc, for the introduction. And first of all, many thanks to Kevin and his team, Stijn and Gino, for inviting me, for having me here. Thanks a lot, it's very much appreciated. I'm a catalytic chemist. I'm working here in Leuven in a Center for Surface Chemistry and Catalysis. First of all, I want to acknowledge a few of the people who have helped me a lot over the years in this hop chemistry. That's Bart Steenakkers, who recently got his PhD, Luc, whom all of you know, and Pascal Mertens. I'm in catalysis, and what is catalysis nowadays concerned about? Especially catalysis for, let's say, organic reactions. Catalysis is very much about doing reactions, transformations in fewer steps, less steps. We will see a very clear example of that. With less waste production also, with eventually higher yields of the desired product, with better selectivity in many cases also, and ideally you can also remove the catalyst easily from the reaction products. You can do a separation of something which preferably is going to be a solid catalyst. I'm not going to tell you how I ended up in hop chemistry, but I did. But we will directly go to the chemistries that we are going to discuss today. You all know, of course, about the utilization of hops in the beer brewing process. An important class of compounds within the hops are the hop resins, and more particularly the alpha acids. The most critical chemical transformation of the alpha acids undoubtedly is their isomerization to iso-alpha acids, which are the bitter principles of beer. I will, in a first experimental part of what I'm going to tell you, speak about this isomerization, how we can do it in improved ways offline instead of using the kettle boiling. Secondly, I will also say a few things about making these compounds more stable, which is known, the tetrahydro, the hexahydro, iso-alpha acids. Also there, I will show to you how catalysis can do the things better. Fewer steps, better yields. Thirdly, and that's not even catalysis, but still, I'm going to discuss some chemistry of hop oil, namely of the sesquiterpenes that we find in hop oil, and I'm going to focus on oxygenation processes of hop oil compounds, specifically epoxidation, but that will become clear later on. So let's first turn to this first step, to this first reaction that I'm going to discuss, the isomerization of the alpha acids. Alpha acids are just one of three main groups of compounds in the hop resins. Actually, there is the alpha acids like humulone, there is the beta acids with one prenyl chain more, and there are also the chalcones, the flavones like xanthohumol. I'm only going to discuss the alpha acids, and as I told already, these need to be isomerized in the brewing process. If you do it the classical way, actually, this will happen just during the wort boiling, which is something which happens at a pH of 5.2 and in aqueous conditions. So in aqueous conditions at a slightly acidic pH. One of the problems already is that the dissolution of these alpha acids will only be partial. A second thing is that actually these acidic conditions are not the most suitable ones for affecting this isomerization of alpha acids to iso-alpha acids like this isohumulone. You see that this is the contraction, in fact, of a 6-ring, of this 6-ring fluoroglucinol to a 5-ring. In fact, this is an alpha-ketol rearrangement, like we would tell it. It's not a perfect process. The utilization eventually is limited. 45% is maybe a good estimate. Also, side products and side compounds are formed. Of course, this has been studied before, and people have been isomerizing these alpha acids offline, which actually comes down to the fact that they use extracts, typically the supercritical CO2 extracts, which also contain these alpha acids, which are then offline isomerized. Essentially, what people do is to make them soluble first by adding a base like potassium hydroxide, then some magnesium compound is added, and that produces, in fact, an insoluble magnesium humulate, which will then be converted at higher temperature to an insoluble magnesium isohumulate. So one of the problems is that you need the magnesium to actually to promote this isomerization, but this also produces something which essentially is insoluble. If you want to work on with this compound, you will have to convert it back to the acid. This will become clear in the next step. So the eventual result is that, in fact, because you go to the magnesium salt, because you have to acidify afterwards, you have production of salt waste, and that's something that I, as a catalytic chemist, do not like. So this is the overall process. In fact, you start, for instance, from this alpha acid. You make it soluble by making the magnesium salt. Then at higher temperature, you have the isomerization. 6 ring goes to 5 ring. Then you have to acidify, and eventually you have to use potassium hydroxide again to convert this thing to a potassium salt, which is much more soluble. It's a multi-step process. It generates waste. The question that we asked ourselves at this beginning was, can we do this actually in one step? Can we devise catalysts that would do a one-step transformation of this 6 ring to this 5 ring? Or even better, to a 5 ring, to an iso acid which is quite soluble. Can we do this? Well, we set off with just looking at catalysts. And catalysts for me often means solid materials, heterogeneous catalysts, powders that you throw into some compound, some solution that you can recover by filtration afterwards. Heterogeneous in the sense that they are heterogeneous phase-wise, that they form a separate other phase during the catalysis, and also at the end, which has the advantage that you can recover them quite easily. We somehow started off with the magnesium compounds, with insoluble magnesium compounds, minerals as a matter of fact. This is the blank reaction. In these conditions, isomerization of the alpha acid to the iso-alpha acid, even the blank somehow works, and after quite some time, 18 hours, you get 12% of conversion. Addition of these magnesium solids actually gave sometimes hardly any improvement over these blank reactions, but sometimes the improvement was clear, like a spinel, which is essentially an insoluble magnesium aluminum oxide, gave 20% yield, with still a very high selectivity for the isomerized alpha acid. If you look at such spinels, actually these are crystalline materials with very well-known crystal structures. What is this material, for instance? Well, actually, the yellow tetrahedra are surrounding aluminum, which is sitting here. The green octahedra are surrounding magnesium, and the basicity is actually originating from these oxygen atoms in this lattice. This is just a crystalline material, a mineral like you would have quartz. Well, this is the mineral spinel. It's basic. It has basic sites, basic oxygen atoms at its surface. We then found out actually that if you started to vary the nature of these cations, for instance, if you exchanged magnesium for calcium and strontium and barium, that you got a much more active catalyst and a much better yield already also. In comparison with the 12%, we got up to 51% of yield of the isomerized acid after 18 hours again, and with still a very high selectivity. We could also trace this back to the titrated basicity of the material, etc. Maybe not so important here. But we could even further improve upon this. How? Because, well, actually, if you think of such crystals, the crystals may be large, the crystals may be small. If they are large, there is not much outer surface to these crystals. That means that there are not so many exposed oxygen sites, oxide anions, which will do the reaction. We then resorted to techniques of making these crystallites very fine, which brings you to the idea of a high surface area material, a nanomaterial, people would call it nowadays. We found out that a high surface area barium aluminate actually catalyzes this reaction in very high yield and with very high selectivity, because we have a very high surface area. So, is this catalyst then reusable? Because ideally a catalyst should be reusable. Actually, yes. If we filtered this catalyst from this reaction medium, if we reused it, we saw that in consecutive runs, the yields were consistently above 90%. Actually, this transformation in the conditions like described here is already complete nearly after 10 hours. You see that the yield goes steeply up until you get close to this eventual yield of 94%. So, first, clear conclusion, we can indeed devise solid recoverable catalysts for this transformation of an alpha acid to an iso-alpha acid. It would be even better if immediately we also somehow transformed this alpha acid to a very well soluble form, and therefore we will have to produce the anion with probably a cation which solubilizes very well this iso-alpha acid, this humulate. How could we do this? Well, we went on actually to screen the effect of nitrogen bases on this transformation, on this isomerization, for instance, of alpha acids. If you add a base, a nitrogen base, B, then eventually you will obtain a product which is in the anionic form, but which is ion paired with the protonated form of the base, hence BH+. We screened many, actually really many. We found out actually that for instance, from these heterocycles, from these nitrogen heterocycles, the true aliphatic bases, the strongest amines are also the best catalysts. Like for instance, piperidine, like pyrrolidine, with which you get a yield of already 25% in comparison with a blank, which in these conditions gave 8% of the isomerized yield. Which means that you will have a pyrrolidinium cation here, which will ensure a much better dissolution. Here it's not so trivial to get the catalyst out. And of course that's something that you normally want to do. You want to recover the catalyst. But do we need to get the catalyst out? Well, actually in the next version of this technology we don't. Why? Well, we went on to screen natural compounds. Compounds that you could leave in the beer if you wanted. And you see of course that this pyrrolidine, is very much similar to an amino acid, proline. So we found out that if you just mixed proline with an extract of the alpha acids, and if you then heat it a bit and so on, and you wait for 6 hours, you already get a much better yield of the isoalpha acids. You go up to 31% of the isoalpha acid in the presence of proline. We tested many other compounds. I'm not going to discuss them in detail. Anyway, proline, the nice part about it, of course, is that you can leave it in. Of course, after the isomerization, the proline will be present as a prolinium cation, but you can leave it in. Essentially, what you make is the anion of an isoalpha acid, ion paired with prolinium. You can leave it in. You can just dilute it as such into the beer that you are brewing. Proline actually was not such a surprise. I didn't choose it by coincidence. Why not? If you would be familiar with the literature of, let's say, catalytic organic chemistry, you would know that there has been a huge wave of proline catalysis in organic chemistry. Why? Because proline, for instance, is a quite effective catalyst in non-aqueous media for a range of nice reactions like enantioselective selective aldol condensations and so on. So let's say, looking from the viewpoint of organic chemistry and from catalysis, choosing proline is very natural, but of course in the brewing science it's a bit unusual that you would mix precisely this proline with alpha acids to affect the isomerization. If you extend the reaction time a bit, actually you can get to isoalpha acid formation, to isomerization in very high yield. After 20 hours with a 1-1 mixture of proline and with the alpha acid, you get to a 96% isomerization yield. Even if there is some beta acids present, this will not hinder the isomerization. This is also a technology which we patented, which was also mentioned in one paper that we wrote recently. And actually we have newer versions of this technology even in the pipeline, but I'm not going to speak about that today. So the isomerization can actually be done in various ways, either with a solid recoverable catalyst, or we can do that with proline as a natural food-compatible isomerization agent. A second reaction, a second type of chemistry of hops that I'm going to briefly discuss with you, that is the stabilization of these isoalpha acids. This is well known, since all the seminal contributions of, for instance, Dennis de Keukelaere, it's known that isoalpha acids are liable to degradation. In the presence of acid, then you get these nice complex polycyclic compounds. Or in the presence of base, and that's an important one, because in the presence of base, you see that you get a dealkylation, which is of course very much undesired. But the most dangerous of all is probably the light-induced decomposition of these isoalpha acids. Why? Because you get a radical fragmentation of this relatively weak bond, in the sense that you get them, for instance, this carbonyl radical, which will decompose, which will lose CO. Eventually, if the resulting alkyl radical meets a sulfur compound, you will make this skunky thiol, which is very much undesired. There are solutions for that. There are classical solutions for that, partly from the field of catalysis. For instance, there is technology to convert isoalpha acids into the tetrahydro form, in which actually these double bonds, the CC double bonds, this one and this one, are hydrogenated to single bonds. That's fine. That's done with a catalyst. Palladium and carbon, standard technology, very much applied. But what you would also really want to have a light stable isoalpha acid is to not have this labile alpha hydroxycarbonyl fragment here. And to eliminate that, people have since quite some time been using what we would call not catalytic chemistry, but stoichiometric reactions with sodium borohydride. This is effective. This will indeed selectively reduce the carbonyl to an alcohol, but there is a downside to it, namely that the borohydride will also give rise to borate waste, and you have to do a lot of separation processes, sometimes even with hexane, to isolate eventually these hexahydroisoalpha acids. So also here the question was, can we actually do this transformation of isoalpha acids to the hexahydro form? Can we do that in one step? And the answer is yes. If you look to another type of catalyst than the classical palladium carbon, we did this with ruthenium carbon, which eventually turned out to be the best solution. Ruthenium carbon is a catalyst which in even food technology is used a lot. If people nowadays in a sorbitol plant make sorbitol, this is very often done just by hydrogenating glucose with ruthenium carbon, aqueous conditions, water, and so on. So our idea was maybe we can also use this catalyst for this transformation of the isoalpha acid to the hexahydro form. And actually, if you look at the course of this reaction, the blue curve is the iso acid, the red curve is the tetrahydro isoalpha acid with actually the single CC bonds, but we do indeed after some time also form in high yield the hexahydro isoalpha acids. So it turns out that this ruthenium catalyst is capable of both hydrogenating carbon-carbon and carbon-oxygen double bonds. So it's a catalyst which really does both. It does it sequentially, implying that it has a higher affinity, a higher reactivity towards carbon-carbon double bonds, but eventually you do also, like in the glucose to sorbitol hydrogenation, you do also hydrogenate this CO double bond to an alcohol. A catalyst which is also perfectly reusable several times. So ruthenium carbon as a new catalyst for CC and CO double bond hydrogenation, giving high yields of hexahydro isoalpha acids. What's the big advantage of using catalysis here, of using new types of catalysis instead of having these two steps with first palladium carbon, then with the sodium borohydride? You do this now in one step with just hydrogen. No separation issues of the residues of the borohydride and so on. So it's much cleaner and also very good yield that you obtain with this procedure. And then finally, if I have time, but I guess I have, still a few minutes, I'm going to say a few things about the things we did in hop oil chemistry, especially the sesquiterpenes. We all know that hop oil contains terpenes like myrcene, but also sesquiterpenes like caryophyllene and alpha-humulene. And it's known also, it has been claimed that especially the epoxides of these olefins play a big role in forming the hoppy aroma of certain hops. So the epoxides are often found, they're often analyzed, and there are many reports, mainly by Deinzer, for instance, also relating the hoppy aroma to the presence of these epoxides. Now, for me as a chemist, this is interesting because an oxidation with dioxygen of an olefin, for me, does not give necessarily only an epoxide. Yet there are many claims that the epoxides are the main products. It's a chemistry which essentially was not understood. We did this chemistry. We looked at, for instance, the autooxidation of beta-caryophyllene, and we saw indeed that the epoxide was formed with high conversion. We tested many systems. Actually, you see in the autooxidation of neat caryophyllene, you see very much the same product distribution, the same selectivities and so on. Then when you do it in a solvent, like for instance acetonitrile, which you would not use in brewery, of course, but here our interest was really in understanding this epoxidation of beta-caryophyllene, but using oxygen. So we have a high conversion. The main products are indeed the beta-caryophyllene epoxide, but also the isomer, so the isocaryophyllene epoxide. We also found some side products, which I will detail in a few minutes, but why is this such a surprising find? Or why is it so surprising to see that of all the products formed, the main fraction, in fact the selectivity, amounts to 73%. So 73% of the converted caryophyllene actually is converted to the epoxide. Why is this surprising? Many of you will be familiar with the autooxidation of fatty acids like oleic acid. And you know that these are radical chains. And in such a radical chain, one of the ideas is that you make intermediate species like this peroxo radical. And actually this peroxo radical can affect epoxidations. It can transfer an oxygen atom to another molecule of the olefin so that eventually you end up with an epoxide and with a leftover product. And that's maybe the essence. Indeed, normally autooxidation, like you have with fatty acids, is capable of producing epoxides, but each time for every molecule of epoxide that you produce, you should also find a leftover molecule. Therefore, it's very surprising that in this, autooxidation of beta-caryophyllene, you would find epoxide selectivities which are higher than 50%. Yet we did. So we found these epoxides, the main epoxide, the isomerized epoxide. We also found some surprising byproducts, like for instance this dicarbonyl compound, which was clearly there in quite small yields, but it's clearly there. We also even found the isomerized caryophyllene, and we also found the double epoxide, which is not that surprising. We did a lot of experiments to understand this. I'm not going to go into all the details. We found, for instance, that this only works in solvents which are either in neat beta-caryophyllene or in polar solvents. Then that works very well. If you go to apolar solvents, it doesn't work. If you go to protic polar solvents, it doesn't work at all. The conversion of this beta-caryophyllene in autooxidation conditions is very low. The reaction only seems to work in these aprotic polar solvents, like, for instance, ethyl acetate or acetonitrile and so on. We did many experiments, and that's maybe of less interest for you, to elucidate how this actually works. I'm not going to discuss them all in detail. For instance, we found that these radical traps, like the butylated hydroxytoluene, actually inhibited the reaction. You can see that here in the reference autooxidation after 3 hours, we have 13% conversion. If we add this molecule, we have almost no conversion, and so on. We did many other interesting finds. For instance, we found, I'm just going to highlight this one, that if we added a 1-electron oxidant like a cerium-4 compound, that in the presence of this 1-electron oxidant, first of all, the reaction goes much faster. Instead of having just 13% conversion after 3 hours, you have 87%. And then even more surprising, if you do then the reaction with this 1-electron oxidant under nitrogen, you make a different product, namely the isomerized olefin. I know it's a lot of chemistry and a lot of detail. I'm just going to show you how eventually we think that this oxidation is proceeding, this autooxidation, and why it is so special. So autooxidation of beta-caryophyllene, the typical hop sesquiterpene, or of humulene. Actually, humulene is even more typical, but the mechanism is just the same. What happens is special. The reaction is very different from the regular autooxidation like you would know it for instance, oleic acid. Actually, the reaction, because of the very special conformation of this olefin, starts with a single electron transfer to oxygen. You make a superoxide anion, and you make this radical cation. That's the first step. What actually can happen then, if you are not under oxygen atmosphere, if you are under nitrogen, then this radical cation can react with another molecule of beta-caryophyllene, and the result eventually is a chain mechanism which gives you selectively the isomer of caryophyllene or of humulene, if you want. So that already explains why sometimes we see this isomerized olefin. But actually, if you work under oxygen, the radical cation is going to react with dioxygen. You make a couple of intermediates, and eventually we postulate, and we're pretty sure that we make this special molecule, which is a 4-ring with 2 oxygen atoms inside, which is pretty unique in oxidation chemistry. Actually, it's a dioxetane, and we think we're pretty convinced, and all the argumentation can be found in this paper. We are pretty convinced that the dioxetane actually can explain the presence of these dicarbonyl compounds, because actually if you heat a dioxetane, this will just spontaneously split, and you make the dicarbonyl compound, like we have also found it actually in detailed GCMS analysis. But on the other hand, if there is an excess of the caryophyllene present, the dioxetane will act itself as an epoxidizing agent, which is kind of special. While doing so, the dioxetane will lose 1 oxygen atom and will itself be transferred to the epoxide, but it will also transform another beta-caryophyllene molecule to another epoxide molecule. So essentially, this reacts with beta-caryophyllene to 2 epoxide molecules, which explains why we have such a very high selectivity for epoxide formation, and which also explains why indeed in hop oils we often see such a high abundance of the epoxide from humulene, from caryophyllene, without seeing all the byproducts that normally you would expect from a spontaneous radical-induced autooxidation of olefins. So that brings me to the end. As a few conclusions, for the isomerization, we have developed several technologies for the isomerization of alpha acids, either using solid catalysts or using natural compounds like amino acids, proline, which will give you high selectivities of the isoalpha acids. We found that in the reduction of alpha acids or isoalpha acids to the hexahydral compounds, you can shorten the trajectory. You can just replace the 2 steps by 1 single catalytic hydrogenation step. Finally, for the epoxidation of beta-caryophyllene, we found that this is a pretty unique mechanism starting with an electron transfer, which indeed transfers beta-caryophyllene, but also humulene eventually in high yields to the epoxides. Thank you for your attention.
Yeah, I have a question about your chemistry. So you wanted to use a catalyst for the isomerization and end up with soluble isoalpha acids. So you decided to use an organic base, and it was pyrrolidine, but that's a base, of course, I agree, but proline is not a base. So you wanted then later on to replace your first chosen organic base, but you have replaced it with an amino acid. That's not a base.
Well, that's a very good question. Proline would not be considered a base if you work in water, because then, of course, we have a zwitterion. Okay? But if you use proline in non-aqueous conditions, which will not be done in food chemistry normally, but organic chemists do it nowadays all the time, then people know very well that in an organic medium, proline is working differently. And actually, it does work as a base. So the pyrrolidine in proline works as a base, and it's not really, this idea of a zwitterion doesn't hold in an organic medium. If you are in an organic medium, you can be by no means sure that there will be indeed always this proton transfer from the carboxylic acid. That's not how it works. They exist separately, which means that your carboxylic acid is somehow working independently, let's say as a proton relay station. So this means that this carboxylic acid is hanging around somewhere and will at some stage protonate an intermediate. But in an organic medium, and there's a lot of literature about it, but it's pretty recent literature, it's organic literature in high-level chemistry literature, let's say, which will show you that this is really working as a base and that you have a proton assisting in, let's say, some base acid catalytic mechanisms, like aldol condensations. I mean, the reaction for which proline really came to the foreground in organic synthesis was aldol. Aldol is something that you would associate with base, but then aldol in an enantioselective way. Why would this occur in an enantioselective way? Because the carboxylic acid, which is hanging on this pyrrolidine ring, is somehow organizing the reactants so that they do the aldol condensation in an enantioselective way. It's a good question, but yes, proline behaves in non-aqueous media, like in pure alpha acid, because that's non-aqueous, that's how we do it, behaves not as a neutral compound, but behaves as a base. Thank you.
Professor De Vos, thank you for your presentation. I have one question that relates to the impact of this kind of technology on the alpha supply and demand balance in the world. What is the impact, and how do you propose to monitor and manage this as you introduce the technology?
Well, I think the main impact is of course in the utilization and also in the dispersibility of the isomerized alpha acids into the beer eventually. I think there are several new ideas here. The main impact is probably that with many of the pretty well established magnesium technologies, potassium hydroxide is also used as an agent or as a catalyst. I think it's rather an agent for the transformation. And potassium hydroxide, after all, is a pretty harsh base. It will cause side reactions of various types. I think you know them, maybe even better than me, but it does cause side reactions. I think that with, for instance, the proline and with these milder organic bases, we hit like the right spot of where you need to be in terms of having effective reaction, but without doing the side reactions. So yes, you go to a more effective utilization, first of all, because the chemistry is better. The chemistry is better, it's more adapted to working in, let's say, this organic background, this organic matrix of an alpha extract. That's one element. Second point is very clearly in a better dispersibility, a better solubilization of the compounds, of the prolinium iso-alpha acid association. So I think this really can lead to a much better utilization. Clearly, proline is something which is naturally also present in beer and can even be metabolized, if we are correctly informed, by some yeasts. So, yeah, you can just throw it in directly. We will have to see the impact. I'm mainly interested and intrigued, and I think 25 minutes is enough to focus on the chemistry. We will see what the impact is. But I think that technically, I consider this problem as solved. I mean, if you take an alpha acid product, an alpha acid, and you can just mix it at high temperature with proline, which is a stable and completely non-noxious compound, then I say, okay, now let's look to something else, because this is a solved problem. This is a solved technology.